Let's do a two-dimensional example. So here we've got a function f of xy is x squared minus y squared, and we're looking at it on the unit circle inside. We're looking at the part of the region x squared plus y squared is less than or equal to 1. So we'd like to find the maximum or minimum of this function. So first, we look for gradient, for critical points on the inside. The circle itself has an interior, and so we look for critical points. The gradient of f is 2x comma 2y. The only way we have a critical point is if 2x equals 0 and minus 2y is equal to 0. The only way that happens is if x is 0 and y is 0. So 0, 0 is the only critical point right at the center of the circle. And we can apply the second derivative test. Let's look at the Hessian. The Hessian is the matrix of second partial derivatives. The derivatives of 2x are 2 and 0. The derivatives of minus 2y are 0 and minus 2. And so this is our Hessian matrix, 2, 0, 0, minus 2. The determinant of the upper left-hand corner is positive, and the determinant of the whole thing is negative. That's not positive positive, so it's not a local max. And it's not negative positive, so it's not a local min. And it doesn't fall off the edge and eventually turn into 0. That means it's definitely a saddle point. So actually, the point at the middle is the only critical point, but it's not a local max or a local min. That means that the global maximum and global minimum of this function have to be on the outside boundary. So to find the max and min, we have to parameterize the boundary. The boundary is a circle. We know how to parameterize circles. We can parameterize it by c of t is cos of t comma sine of t for time t between 0 and 2 pi. And then we plug that into our function f of c of t. Our function f of xy, remember, was x squared minus y squared. And so we plug in x is cos t and y is sine t, and we get cos squared t minus sine squared t. And it's going to make our lives a lot easier if we remember a double angle formula. Cos minus sine. Sine is the same as the addition formula, and so this is the same as just cos of 2t. And so then we want to find the maximum or minimum of cos of 2t. And that's now a single variable maximization minimization problem for a function of one variable. We find its derivative, negative sine of 2t times 2 by the chain rule, and that vanishes. Sine vanishes at the multiples of pi, so 0, pi, 2 pi, 3 pi. So sine of 2t vanishes at half of those, 0, pi over 2 pi, 3 pi over 2, and 2 pi. Those are the places where the derivative vanishes. Those are our critical points. And the values of our function at those points are, well, if I plug in 0 to cos of 2t, I get cos of 0. That's 1. If I plug in pi over 2 to cos of 2t, that's cos of pi. That's minus 1. And so on and so on and so on. So the values of the function at these critical points of the one-dimensional region are 1 and minus 1. And normally, we'd have to check the boundary as well. I'd have to check t equals 0 and t equals 2 pi, but I already kind of did that. I plugged in 0 and 2 pi and found that the value was 1 at both of them. So we've already finished that step. And so the global maximum, the biggest this function ever gets, is equal to 1, and the global minimum, the smallest this function ever gets, is minus 1. So that concludes this example.